So, in the last lecture we showed that the liquid phase Reynolds number can almost be as large as the gas phase Reynolds number, right. So, the way of stating this is that what will be the nature of the liquid phase boundary layer. Remember that region 3 that we mentioned within the droplet. Another number that is of practical relevance is the Peclet number. Peclet number is what? U liquid into d by alpha. This d can be the droplet diameter, it can be the radius of the droplet also. This Peclet number is normally much greater than 1. Okay. In fact, this is of the order of 1000 actually, the liquid Peclet number. Okay. And the Prandtl number of the normal liquids are of the order 10 usually, they are not of the order 1. So, in the liquid phase what do you expect? In the liquid phase you expect to see a thin viscous layer, right, and you can get thinner thermal layer. So, thin viscous layer and thinner thermal layer. Now, the Peclet number as I said is of the order of 1000. Okay. So, the liquid flow velocity plays a major role and the Prandtl number is of the order of 10. Okay. So, thinner thermal layer comes because of this Prandtl number, okay, and the thin viscous layer comes because the Peclet number value is high. Okay. So, that is the liquid phase description, right. So, it will also have a boundary layer, that is the bottom line. It will also have a boundary layer. In fact, in most cases the thermal boundary layer is much thinner. Okay. Now, let us now return to the two corollaries or postulates that we mentioned. One was that there is no torque, right. The other is that the friction force is of the order of 1 over the Reynolds number, right. So, these were the two postulates. Okay. So, in a droplet normally you expect a balance to happen between inertial force and friction forces, right. In a droplet one normally expects a balance between friction and inertia, right. So, from an order of magnitude perspective, this is your inertia, this is your friction force, which can be written like this, right. Delta is nothing but the gas phase boundary layer thickness, right. And if you have done your fluid mechanics course, you will find that delta is always scales as R and Reynolds number to the power of half, right. This is from the boundary layer scaling. If you recall, this comes from delta by R scales as Reynolds number to the power of half. If you have done your flat plate boundary layer, you will see that that is the expression that we normally use, right. Okay. So, using that, what you will see here is rho u square scales as tau R by delta, that is tau Reynolds number to the power of half, right. Okay. That is what we are going to get. So, basically it is a combination of inertia and the corresponding the balance between inertia and friction, right. Now, when there is a, as I said, that this asymmetry normally happens due to some fluctuation, right. So, let us go to the next page and write when there is a fluctuation of some kind, okay, this axisymmetry can be lost and the difference in velocity and stress can be found out. So, axisymmetry is usually lost, can be lost, right. Okay. So, what you find is that if you just differentiate the previous form that we had, you will find rho u into delta u scales as Reynolds number to the power of half into delta tau, right. Okay. So, this is just a differential, right. Now, delta u, what is delta u? Delta u can be written as V by neta, and we will see what those V and neta are. Neta is basically the same as the droplet diameter So, this essentially means that the fluctuation, why should the fluctuation in velocity happen? This can happen because of turbulent eddies, right, of different sizes. Now, the turbulent eddy of the pertinent size in this particular application is of the size of the droplet diameter, right, because that is what the droplet can see, right. So, it is a scale thing, it is a scale issue. So, this is basically nothing but the size of the eddy, size of the turbulent eddy. Okay. And v is the corresponding velocity of that eddy, so to say. Okay. So, that is the fluctuating eddy. Okay. This is normally this assumes that this eddy lies in the Kolmogorov scale. We are not going to go into deep what Kolmogorov scale is as of now. Okay. So, this is the scale, this is the smallest scale in the turbulence spectrum. Okay. So, in the Kolmogorov scale, okay, this eddy size is the same as the droplet size, and the velocity of that eddy is given by that v. Okay, and that is the expression that we have. Now, the friction force, what can we write about friction force? Friction force scales as tau into r square, right, is not that so? It is the torque into the corresponding r square. So, the change in the friction force is basically given by r square into delta tau. Once again, it is a simple differential, right. So, the torque on the droplet, what will be the torque value on the droplet? The torque value on the droplet is basically r into this delta f, right, the change in friction, that is basically given as r cube into delta tau just by substituting the expression for friction, right. Now, already this delta tau expression is linked here as we know, right. So, this tau is therefore given as rho u square or rho uv, whatever you call it, Reynolds number to the power of half into r square. Okay. Got it? Okay. So, now the moment of inertia is the torque, right, moment of inertia of a droplet is given as I is rho L into r to the power of 5. Okay. So, the angular acceleration that happens is basically given as T by I, which is also given as rho by rho L. This you can write it if you want as u comma v, that would be the correct way of writing it. Okay. So, this rho by rho L into u into v, Reynolds number to the power of minus half r. Got it? So, that is the angular acceleration. Okay. So, the angular acceleration can also be therefore written as rho by rho L divided by Reynolds number to the power of minus 3 by 2 into 1 by some t residence time square. Now, this t residence time is nothing but the time required by a gas parcel to pass the droplet. Okay. And this residence time, as you can rightly guess, it can be given as r by u, r being the relevant non-dimensional, r being the relevant diameter, right. So, with u, that is the traversing time that the thing actually takes. Okay. So, the tau residence time is this. So, the angular acceleration that is created is basically equal to 1 over the tau residence time. Okay. Now, this omega, the angular acceleration, is roughly constant, right. So, we define time for one rotation as t rot. Okay. So, this implies T rot by T res scales as rho L by rho Reynolds number to the power of 3/4, right. Normally this will be greater than 1. Why? Because rho L is much greater than rho, right, and Reynolds number we have said just now that it is of the order of 100, right, for this kind of a situation. So, naturally the rotation time and the residence time, this is much greater than 1, right. So, this would imply that the T rotation is much greater than the T residence for most of the cases, because this is of the order of 1000. We can estimate this in fact, that T rot by T res is almost equal to 1000, and if the Reynolds number is 100, so it is of the 100 to the power of 3/4, right. So, it will be like several orders higher. Okay. We would expect this to be several orders higher than this, right. Okay. So, at least 3 to 4 orders higher, right. So, the T rotation time is much longer than the T residence time, which justifies our assumption that we said that if the droplet rotates, it rotates so slowly, right, that many gas parcels actually passes over it. Okay. So, there is no asymmetry as such, okay, because this is a very slow process. Okay. On the other hand, we also defined that, let us look at the nature of the friction force. So, the friction force delta F by F basically scales as 2 by Re, right. So, this also shows that the delta F is basically of the order of 1 over Re. So, if Re is very large, the change in friction force is very small, percentage change is very small, because Re is of the order of 100, right. So, delta F by F should be like of the order of 50. That means, the change in friction force is roughly 50 times lower than the value of friction. So, there is a, what we can say, there is a small change in friction, right, and long rotation time. So, we have proved through our scaling argument that that is true. So, the rotation or asymmetric circulation is not significant for droplets with large Reynolds number values. Okay. So, whatever we portrayed in that PPT, where we showed that what are the regimes within the droplet, that is still valid. We can take it to be axisymmetric, nice and axisymmetric. Okay. So, that would be the first thing, okay, and there is no rotational effect. So, we can safely do the problem as if the flow is axisymmetric and there are no rotational effects, got it. Okay. So, now that we have done it, now let us look at the first level of analysis. That means, we would now start to look at the approximate analysis of the gas phase boundary layer. Okay, gas phase boundary layer. So, we are first going to analyze the gas phase boundary layer, because that is step number 1. We have to also come and do the liquid phase analysis, because this is a full convective model that we are looking at, right. So, the first assumption is basically that your Reynolds number of the droplet is greater than 1, which is obvious, because that is when the convection becomes an important part of the whole thing. And we are assuming that thin boundary layer exists on droplet surface. This is already established, but we are putting this as an assumption. We are going to neglect viscous dissipation, and we are going to assume Prandtl number equal to Schmidt number is equal to 1. Okay. Xy in our expression means, x means the tangential to the droplet surface, okay, and y means normal to droplet surface. Got it? Normal to the droplet surface, okay, and r designates distance from axis of symmetry. Okay. So, R equal to capital R basically means the droplet surface. Okay. So, these are the for the approximate analysis of the gas phase boundary layer, these are the few assumptions, not assumptions per se, okay, or are very valid. Okay. So, based on this we can start working on the problem, and here what we will do is that we will take abundant use of the existing literature that is available on gas phase boundary layers, say over flat plate. Say for example, a droplet can be now analyzed like a flat plate boundary layer or like a stagnation flow. Stagnation flow is like this, as you know, right, that is called the Hyman's flow, and there is the flat plate boundary layer. So, combining these two, and also if you know the Falkner-Skan type of solutions, that means any angle, if you have a surface inclined at any particular angle, there is a class of solutions that are available which are called the Falkner-Skan. Okay. So, that looks like a Blasius solution, but it is applicable for any level of inclination. Blasius solution is only available for a flat plate, right, with 0 pressure gradient, right. In the case of Hyman's flow it is different, and this Falkner-Skan basically includes these two as two special cases. Okay. So, Falkner-Skan is applicable for any wedge, right, whatever the magnitude of that wedge is, right. So, when the wedge becomes 90 degree, it becomes basically what we call a Hyman's or a stagnation flow. When it becomes 0, it becomes like a flat plate boundary layer, right. So, a droplet basically what we are trying to say over here, it can be actually resolved, you know, in pieces, and locally it can be made to approach a situation like this. One way it can be like a flat plate, one way it can be like a stagnation point, and in between the curvature changes, right. So, it is almost like these wedges. So, if you take this section out, you will find that is like a wedge, right, it is like a wedge of a certain angle, got it. So, we can use locally Falkner-Skan class of solutions to solve the boundary layer, right, because it is a droplet with pieces, right, in pieces in locally, right, it behaves like a Falkner-Skan class of solutions. Okay. And there are extremes like this and this, where it behaves like a normal flat plate boundary layer or like a stagnation flow solution. Okay. So, let us write the equations which will be useful. So, continuity, good part is that we do not have to solve all of them, but the math we are not going to work out the math like that, but we are just going to pose the problem, and we have already explained how the problem can be solved. So, it requires that Falkner-Skan type of solution. So, that is the continuity equation, x momentum equation, and you will find a lot of similarity with your flat plate boundary layer. We will say what UE is, just hold on for a second till we establish these equations. Where do you recall that this comes from the Euler's equation in outside the boundary layer, right. So, UE is basically nothing but the potential flow. Flow velocity outside the boundary layer. This we already knew, right, from your, if you recall your classes where we actually did this Falkner-Skan type of solutions or whatever courses that you may have taken. This is the solution, this is basically comes from the Euler's equation, which basically relates the pressure gradient with the velocity, right. This is Euler's equation. If you look at the x momentum equation carefully, you will find that there are variations of u with respect to x and y. There is an additional term that we are carrying over here, which solely comes because there is a variation of the free stream velocity, or basically variation in the velocity UE, that is the velocity outside the boundary layer with respect to x. There is a spatial variation, right. Once there is a spatial variation, this term has to be included, because its origination, this is also true in the case of your Falkner-Skan and other things. Okay. So, that is very important. Okay. And what about the y momentum equation? Now, the y momentum equation, the pressure gradients in the y direction is negligible. Gradients in y direction is negligible, right. So, this particular term on the other hand, this term that we have mentioned, okay, this has got a peculiar feature. For example, at the edge of the boundary layer, this term becomes equal to 0, right, because at the edge of the boundary layer it becomes equal to 0. It is also negligible at the droplet surface. At droplet surface, it is negligible. Okay. Why it is negligible at the droplet surface? Because the transverse variation of the dynamic pressure is small at the droplet surface. Transverse variation of the dynamic pressure is small at the droplet surface. So, this term also has got a particular feature, that feature being that it is negligible at the droplet surface, and at the edge of the boundary layer it becomes equal to 0. Okay. That is because these two terms becomes equal to 0 to each other, I mean they become 1, right. So, they become equal to 0. Okay. This term clearly drops out. Okay. So, based on that, so that is the part. So, there are two special cases, of course, as you can see that it is tough to solve it, okay, holistically. So, we will take two cases, two cases needs to be taken. First one is basically the stagnation point flow, where R is equal to x and UE equal to AX. You already know the stagnation flow. If not, just do a very quick recap of Panton or FM White's fluid mechanics book. For you can actually read the part on the viscous flow, and there will be flows like stagnation point flow. So, like stagnation point flow is very common. So, one is a stagnation point flow, and you can guess which part is a stagnation point flow. The other one is the shoulder region of the droplet, right. There theta, if you consider theta from the droplet equator, that is at 90 degrees, right. So, theta at 90 degrees, where R is equal to capital R, UE is basically 3 by 2 U infinity. Okay. So, that is the shoulder region, where the pressure gradient in the shoulder region, the pressure gradient is basically equal to 0. Okay. That is exactly like a flat plate. So, the flow locally behaves like a flat plate, and in the flat plate, as you know, u du dx is basically equal to 0, right. That is the flat plate boundary layer, right. Because there is no pressure gradient, there is 0 pressure gradient inside a flat plate boundary layer, right. This you know from your Blasius solution. In fact, that is what the Blasius solution is all about, understood. So, whatever it is, the well known similarity solution, and this we will just use the Blasius form, and you will see that how powerful these things are. The idea is how we can actually take a solution from a very different perspective, you know, and apply it in a very different perspective also, and still get results which are physically very meaningful, insightful results, and that is the beauty of doing fluid mechanics. Okay. So, the similarity solution becomes UEX, and this is F prime neta, where you know that is basically UE into F prime neta, where you know that F neta satisfies Blasius equation. Okay. It satisfies the Blasius equation, and so when you write it, this is basically F triple prime plus F into F double prime is equal to 0. Do you recall the form of this equation? Okay, that is the Blasius flat plate solution, right. Okay. And neta obviously we have to define what is neta, that is R UE. Do not worry about that sign that I have mentioned here, that is basically the dummy variable. Okay. So, that is how neta is actually defined, right. If you do not even get, you just have to recap your flat plate, just go and recap that, okay, if you are not getting the feel of these similarity solutions. Okay. But this is basically a similarity solution and you know what similarity transformations are. So, we are not going to spend time on that. If you have learnt your fluid mechanics, you already know that what similarity transformation exactly means. Okay. So, the vaporization rate per unit area is given as rho V S as minus A F 0, where this A is 2K rho E U E to the power of half for stagnation flow, and this is equal to rho E U E mu E sorry U E by 2 okay, for the shoulder region. Got it? Okay. That is the vaporization rate. Now, the boundary conditions, of course, if you look at the nature of this equation f double prime f double prime equal to 0, how many boundary conditions it needs? It requires 3, right, because it is the triple derivative that we are talking about. So, the boundary condition, 2 boundary conditions are readily available. F prime 0 is equal to US by UE, that is at the surface. F prime infinity is basically equal to 1. This is basically the free stream. These are applied at the 2 boundary layer interfaces, right, and this basically comes from the continuity of tangential velocity at the droplet surface, of tangential velocity at droplet interface. Got it? Okay. So, these 2 boundary conditions, as you can readily see, one is applicable for the free stream when the flow, where basically u approaches the free stream, the other one when it is the tangential velocity where at the droplet interface. In most of the Blasius solution you will find that that will be equal to the 0 because there will be a no slip, right, but here that no slip is not valid. It is no slip, but it is not equal to 0, okay, because there has to be a continuity of that tangential velocity across the droplet interface, and that is very important. Okay. Now, we need basically a third boundary condition, right, third boundary condition is needed. So, in order to get that, let us write the other boundary conditions for energy, say for example. We have not written the energy equation because we have already written it earlier for the gas phase. Okay. So, once again, if you recall what the energy equation was, it is G at the gas interface, gas side of the interface, then this is basically on the liquid side of the interface, right, plus there was this rho Vs which was basically the mass flux into the latent heat. Do you recall? That was the latent heat, right, and this sometimes we wrote it as rho Vs into L effective. Is not that so, right? And then we had a lot of argument regarding the nature of this. This is basically that conduction heat flux, right? Is not that so? That Q dot that we mentioned earlier, right? Okay. So, this is basically the same as spherically symmetric droplet. This is the same as spherically symmetric droplet, right. For species, a similar thing. Once again, we have written it already for the species earlier. We are not writing it once again. Rho Vs YFS minus rho D YF. Sorry, this is not. Okay, and then we have the definition of B is equal to H infinity minus Hs by L effective, right. Okay. So, using all these things, and we are not going to show how because it is very complicated and you also do not have to do it. Okay. Using all these cases, we can now devise the third boundary condition that is needed, and the third boundary condition is basically a little bit complicated to look at. Do not bother about the math because that is not important over here. Okay. It will take a lot of time for you if we have to work out this, okay. That is given as 1 over B, right. So, that is the third boundary condition, okay, which combines the energy, species and everything and uses the definition of B and combines it, and we can have this particular form, right. And let us define the Nusselt number also. So, the Nusselt number is given as this by B Reynolds number to the power of half. Now, this K is not the thermal conductivity. K is basically a greater than 0 non-dimensional coefficient, The order is unity of the order 1, okay, and it is determined when the heat flux is averaged across the droplet surface. This is averaged across the droplet surface, right, across the whole droplet surface, and this K value nominally is given as something like 0.552 into root over 2, okay, about 0.781 or something like that it comes. Okay. Similarly, one can write m dot global, that is the global vaporization rate, is 2 pi k mu E R F 0 into Reynolds number to the power of half. Got it? Okay. So, that is the expression. So, let me write it in a fresh way so that you do not have to. Global is basically 2 pi k. This is not the same k as thermal conductivity, Reynolds number to the power of half, okay. When this k is greater than 0, normally k is about 0.78 something like that, okay, and the Nusselt number, so that you can use it, is given as minus F0 by B into Reynolds number to the power of half. These are the two main factors that even industry people are going to use this again and again, right. Okay. So, this is how we have solved it. Just doing a bit of a recap, we divided the droplet into several pieces, right, and we considered the stagnation flow and the flat plate boundary layer. So, you use the similarity transformation to basically link the velocity and other things, and there we established 3 boundary conditions. The last boundary conditions comes from the energy and the species combining it, and then we have not shown the math that how exactly the steps are. We have devised that there are 2 quantities of importance. One is the Nusselt number, which is for the heat transfer coefficient, and the other one is basically the global evaporation rate. Both are solved in terms of this similarity variable or the Blasius solution, right. Okay. So, with this we have shown that how one of the model would actually work, okay. But there is another type of model which was done by Shiriniano. This does not involve the Falkner-Skan, by the way. So, what Shiriniano and Abramson actually did was that they actually incorporated the Falkner-Skan class of solutions and devised a more rigorous approach to do this, okay. This was not rigorous, this is like ad hoc, it just took like the shoulder region and that the 2 extremities essentially, right, shoulder region and the stagnation region, okay. And so you can assume that all the other solutions will lie somewhere in between. That was the whole argument, right. So, but Shiriniano and Abramson did basically the Falkner-Skan class of solutions using non-zero pressure gradients, okay. And in the next lecture or in the next class we will find out what that exactly is, okay. Thank you.